Let's take a look at some review questions, starting with 5b from the factorials practice sheet. Question asks us to solve for n. The expression we're given is n factorial over n minus 2 factorial equals 20. Let's start by seeing if we can simplify this a little bit. And so what we're going to do is rewrite. And n factorial is the same as n times n minus 1 times n minus 2. And we're going to stop there because now we have a term in our numerator that is equal to the term in our denominator. So I'm going to be able to cancel that out. And we'll do that in a moment. Let's cancel. Goodbye. And so we're left with n, n times n minus 1 equals 20. And this is just going to be a quadratic equation that we can solve. So we're going to have n squared minus n equals 20, or n squared minus n minus 20 equals 0. And now we can use whatever method we choose, whether that's factoring or quadratic equation or whatever, to solve. We can factor this pretty easily. We can express this as n plus 4 and n minus 5 equals 0. So that'll happen when either term goes to 0, either term. So n plus 4 equals 0, n equals negative 4, n minus 5 equals 0, n equals 5. That's all we have to do here. So therefore, n is equal to negative 4 or 5. So those are the values that allow this equation to be true. And we talked previously about finding restrictions, and that just means that our factorial must be greater than or equal to 0. I can't find factorial of a negative number, so we'll just do that as an aside. N minus 2 is greater than 0. N is greater than 2. And that restriction doesn't really matter in this case anyway, because I already found specific values for n, and there was no conflict where... actually, no, sorry, this doesn't matter. N must be greater than 2, so n minus 4 is not a valid result, or we say it's an inadmissible result. So n equals 5 should be our only answer. Next, we'll take a look on the same sheet at 6g. 6 asks us to write each of the following in factorial form. Do not evaluate. And 6g looks like this. So 8 times 6 factorial times 63. And what we want to do here is express these things in terms of their factors. So how can I split up these numbers? Basically, I want to end up with something like 8 times 7 times 6 times 5 times 4, and so on. And so anytime I have a big number, I want to find factors that'll break down and be equal to something like 8, 7, 6, something in that area. So let's see what I can do with 63 in terms of factoring it. And we can try listing our factors of 63 on the side if you find that helpful. So 63 can be expressed as 1 times 63, or 3 times 21, or 3 times 7 times 3, or 7 times 9, or 7 times 3 times 3. And if you look here, I wanted something like 6, 7, 8, 9. I already have the 8, and now I have the 7 and the 9. So let's try working with that. So 8 times 6 factorial times, instead of 63, I'm going to write 7 and 9. And we know that multiplication is commutative. That means the order in which we multiply numbers does not matter. So I can rewrite this as 9 times 8 times 7 times 6 factorial. And remember, factorial just means we'd keep multiplying. So 6 times 5 times 4 times 3 times 2 times 1. And so we can actually just rewrite this as 9 factorial. And if you aren't sure, we can double check with our calculator. 9 factorial is 362,880, and 8 times 63 times 6 factorial is also 362,880. Next, we'll take a look at 6h and apply the same ideas there. So 6h gives us 10 times 7 factorial times 792, I want to break down the big number, so I'm going to start by finding factors of 792. 2 times 396. This term's way too big. I'm obviously going to need larger factors here because I want something in the 10 to 7 range, just to kind of give us a feel for what we're looking for. So we can do like 792 divided by 8. That looks promising. 8 times 99, which is 8 times 9 times 11. And these values all look like a pretty good fit for around here. So let's try rewriting it. 10 times 7 factorial times 11 times 9 times 8. Order doesn't matter, so let's rewrite. 11 times 9 times 8. Oops. 11 times 10 times 9 times 8 times 7 factorial. And we don't have any gaps. We're going straight from 11 down, so I can just rewrite this as 11 factorial. If you aren't sure of your answer, we can put this in our calculator and this in our calculator and compare and make sure we're getting the same result each time. Next, we're going to take a look at our working with cases worksheet, and let's start with number 1. I'm not going to rewrite the question, I'll just read it and write down the required numbers as we go. You have 5 chocolate bars and 4 candies left in your Halloween stash. Your mom has said you can bring 5 things for your weekend camping trip. How many ways can you do this if you want to have at least 3 chocolate bars? And one of the key things to notice here is at least 5 chocolate bars. So I want to think all the different ways I can do this. And so we're going to have our chocolate bars and our candy. And you don't need to do this strictly. We're just doing it for illustrative purposes. What are the ways I can do this? At least 3 chocolate bars. So I can have 3 chocolate bars and 2 candies for a total of 5 items. Or, so chocolate bars and candy. I can have 3 chocolate bars and 2 candy. Or I can have 4 chocolate bars and 1 candy. Or I can have 5 chocolate bars and 0 candies. So what's that going to look like? How are we going to find this? Well, I'm going to have my, basically there's 2 things going on here. First is the and, chocolate bars and candy. So let's see how to find my number of chocolate bars. So I'm going to have how many chocolate bars to choose from? 5. And I'm going to choose 3 of them. And 2 candies. Anytime I see and, it's product rule, so I'm going to multiply. And that's going to be, how many candies do I have to choose from? Well, the question said 4. Choose 2. So this is my first situation right here. And then it says or. Or means it's going to be our addition rule. So let's add. Or 5, choose 4 candy bars, and 4, choose 1 candies, or chocolate bars. And finally, our situation down here, plus, so or, still choosing from 5 chocolate bars. I'm going to choose all 5 as chocolate bars, and 4, choose 0 candies. And now it's just a matter of evaluating. So let's do the math. 5, choose 3, times 4, choose 2 is going to be equal to 60. Plus 5, choose 4 times 4, choose 1 is going to be 20. Plus 5, choose 5 is 1, and 4, choose 0 is 1. So 1 times 1 is 1. So therefore, there are going to be 81 ways of choosing our candy bars. So we had to think about all our possible options, calculate the different outcomes for each option basically using our counting rules that we've learned previously, and then adding them all up to get 81. So therefore, there are 81 ways to bring at least 3 chocolate bars. I don't know if I'm going to take the time to go all through all of number 2, but we'll at least start. Number 2 says, from a group of 5 men, and 4 women, determine how many committees of 5 people can be formed. With A, no restrictions, B, exactly 3 women, 4, or C, exactly 4 men, D, no women, E, at least 2 men, F, at least 3 women. Once again, we can consider what our possibilities are for committee formation. So we're going to have men and women. And let's count our numbers we can have. So we can have 0 men and 5 women, 4 men and 1 woman, 3 men and 2 women, 2 men and 3 women, 1 man and 4 women, 0 man and 5 women. So those are our possible combinations. And I guess I shouldn't use the word combination lightly. Those are our possible breakdowns of men and women. And let's take a look at A. In the first case, there are no restrictions. So we're starting from a pool of 9 people. We're going to choose. There's nothing about order or position on the committee or anything. All I care is who's in the committee. If I threw them all in a bag and jumbled it around, I would still have the same committee, even though they've moved positions. So 9, choose 5. Let's do that on the old calculator. 9 choose 5 is going to give us 126. Question B asks for exactly 3 women. So we can think of this like a binomial thing, because the only options are, actually, sorry, not binomial. This is like hypergeometric, because we are choosing things without replacement. Every time I choose a woman from the pool, there are less women to choose from. So let's label that really quickly. Hypergeometric. The probabilities are going to change as we work, even though, and so the trials are dependent. So it's not binomial, it's not uniform probability. And we want exactly 3 women. So let X be number of women. So success is being a woman. And let's write out our formula. I find that helpful to do right away with these questions and then kind of fill in the blanks. So P of X is equal to ACX times N minus A C R minus X. Oh, and it's not probability. It's just how many ways the committee can be formed. So with probability, we could go over NCR, but I don't need to divide that. I just want the number of favorable outcomes, which is the top part. I don't need the number of total outcomes, which is the bottom. So this will be N of X. I think we can say it that way. Yeah, so what's the cardinality of set X, where X is a number of women? And in our case, we want X to be equal to 3. That's exactly 3 women. So let's take a look. A is our number of successful items in the population. There are 4 women total to choose from, so 4. Choose. How many women are we choosing? Exactly 3, so 3 times how many people are left on the committee to be, or how many people are left to be chosen from? We had 9 in total in our population. 5 plus 4 is 9. We've already used up the women, so to speak. There's only men left, so 5. Choose. How many more people need to be on our committee? Well, 5. We've already chosen 3. So there are going to be 2 left. And now we just do the math. So 4 choose 3 times 5 choose 2 gives us 40. So there are 40 ways of choosing a committee with exactly 3 women. C, with exactly 4 men. So let's keep our same statement as before, our same let statement. Let X be the number of women. So success is being a woman. So we want 4 failures, so to speak. And if we have 4 failures, 4 men, that means there's 1 successful woman. So we're going to find N of X equal to 1. Or we could rephrase the question. We could define success as being a man. That could be our X value. That's fine, but I'm not going to do that. All right. So for the women, how many women am I choosing from? Still 4. Choose 1 times the men. There are 5 men left to choose from, and we're choosing 4 men, like we see here. Let's plug it into our calculator. 4 choose 1 times 5 choose 4 is going to give us 20. Question D, no women. So I want this committee right here. Whoop. I want this committee here. That is, I made a mistake on here. I want the first committee Made a mistake again. I want the first committee. That's 5 men and no women. All right. Once again, I'm not going to change my question. I could set X to be the number of men. I don't want to change that. I'm just going to find when there are no women when X is equal to 0. So 4 women to choose from, we're choosing 0 times 5 men to choose from, we're choosing 5. 4 choose 0. How many ways are there to choose 0 items from 4? There's just one way. So 1 times 5 choose 5. 5 choose 5 is also 1. So there's only one way to choose them because we don't care about the order. We just choose Adam, Billy, Carl, Dave, and Evan. And it doesn't matter what order they're in. They're still the same committee. All right, let's take a look at E. At least 2 women. Here's where it gets a little bit fun. So N of X is greater than or equal to 2. So I need to find the number of ways to have a committee of 2 and a committee of 3 and a committee of 4 and a committee of 5. This is using the direct method, or I can find the committees that have less than 2 women. So I can do 1, so the total probability, all the probabilities add up to 100, so 1 minus N of X less than 2. And so I would find N of X less than 2 is equal to, so N is either equal, so, sorry, my outcomes were X is equal to 1, so there's 1 woman on the committee, or means addition rule, we're going to add number of outcomes when X equals 0. And we're just going to follow the math from above. I'm not going to show that here. I'll just set it up for you and not finish it. F, at least 3 women. Oh, sorry, I misread the question. Let's go back and do E. At least 2 men. So that means less than or equal to 3 women. All right, I'm not going to edit this video. We're just going to go back and fix this. I think what I said made like what I thought the question was, I explained properly, but that's not what the question is actually asking. So let's go back. Let's take a look at number 8. Sorry, at number E. Letter E. E said at least 2 men. So at least 2 men means that our number of women is 3 or less. So X is less than or equal to 3. So we're going to find the number of ways to make the committee when my number of women is 3, or, so add, when my number of women is 2, or when it's 1, or when it's 0. And once again, I'm not going to set that up for you. You can see above how to do that. You can finish answering it. And the last one, at least 3 women. Number of women is greater than or equal to 3. So I need number of women to be 3, or number of women equal to 4, or number of women equal to 5. And once again, we're just doing the same calculations we did up here. You're just doing repeated calculations, 1 for each term in our new questions. Next, we'll take a look at number 3 from the same worksheet. In the card game Euchre, you use only 9s, 10s, jacks, queens, kings, and aces. 5 card hands are dealt. How many Euchre hands contain at least 3 queens? Once again, we're not finding probability, we're just counting. So let X be the number of queens in your hand. And because we're dealing with cards, we're not replacing the cards. Probabilities are going to change as we go. So this is hypergeometric. So let's write out our hypergeometric. Once again, it's not the probability, it's just the top half of the probability equation. We're just counting how many favorable outcomes there are times n minus a CR minus x. All right. A is my number of successes. X is my number of queens, which in this case is number of successes like that I've selected. N is my total population that I'm choosing from. And R is my number of trials. All right, let's take a look. N of X equals, so the first one says at least 3 queens. So X is greater than or equal to 3. So I want to find N of X is equal to 3, or N of X is equal to 4, or N of X is equal to 5. Let's plug in some numbers. So we're going to have A is our number of successes. In other words, how many queens are there in the whole deck? Actually, we don't even need this because there's only 4 queens in the whole deck, so I can eliminate this term. I'll never have 5 queens. It's not possible. All right, that made our life a little easier before we even began. Let's go ahead here. Number of successes in the deck, number of queens in total in the population is 4. Choose our number of queens we're testing for, which is 3. So 3 times N minus A. So the total number of cards we're choosing from is, in a standard deck, it would be 52. In this case, we have 9s, 10s, jacks, queens, kings, and aces. So 6 different types of cards times 4 suits. So N is going to be 24. So 24. Choose, and we're choosing our number of trials is 5 because there's 5 cards in our hand. So every time I pick a card, that's a trial. We've already said 3 of them are queens, so there's only 2 left. So 5 minus 3 is 2. And let's do our next term, plus 4 queens in the deck. We're choosing all 4 of them, times 24 other cards, choosing 1 other card. Now we can calculate. So I'm going to have 4 choose 3 times 24 choose 2 is equal to 1104, plus 4 choose 4 times 24 choose 1 is 24. And I made a mistake. Let's go back and fix that for a moment. So I was right when I said that we have 9s, 10s, jacks, queens, kings, and aces times 4 suits. So 1, 2, 3, 4, 5, 6. 6 times 4 is 24. But I shouldn't have used 24 here because that's all the cards that are left that are not queens. So we need to fix that. Instead of it being a 24, it's going to be 24 minus 4. So it's just going to be 20 because there are 20 non-queen cards in the deck to choose from. So this is everything else besides our successful values. So 24 minus 4 leaves us with 20. Not too bad to fix. Hopefully you understand the reason why we just had to do that. Let's redo our calculation. So we're going to do 4 choose 4 times 4 choose 3 times 20 choose 2. So we're going to get 760 plus 4 choose 4, which is 1, and 20 choose 1, which is 20, and therefore we get 780. Therefore, there are 780 ways of drawing at least 3 queens. To be brief, I'll just set up the other ones. I probably won't finish solving them for question B. At least 2 black cards. So N of X is greater than or equal to 2. Let X be number of black cards in hand. So N of X is equal to 2, or 3, or 4. How many black cards are there to choose from? Well, half of all the available cards are black because half the suits are red, half the suits are black. So we're going to have 12 to choose from. And I'm choosing 2 times. How many cards are left? 24 minus 12 is 12. Choosing the other 3. Plus 12 choose 3 times 12 choose 2. Plus 12 choose 4 times 12 choose 1. And I actually missed a term here because we can have all black cards in our hands. So I missed a term. Plus equals 5. plus 12, choose 5, times 12, choose 0. I'm not going to solve that, but it's easy enough for you to do if you wish. And then question C will be very similar. Finally, number 5, in cribbage, each player is dealt 6 cards from a standard deck of cards. In how many ways could a hand contain at least 2 queens, more than 3 red cards, at least 2 hearts, and at least 2 spades? I'll just point out quickly for 5C, it's an and question, so we're going to be multiplying. So you're going to have to do at least 2 hearts multiplied by the values for at least 2 spades. But we're just going to do 5A for the sake of time. So they're going to receive 6 cards. So the trials, the number of cards we're selecting is 6. For A, we care about the number of queens, so let X be number of queens. Once again, it's hypergeometric. We're dealing cards. Hypergeo. So I'll write my formula out. N of X is equal to A CX times N minus A CR minus X. All right, let's plug in our values. We want at least 2 queens. So N of X is greater than or equal to 2. So how many queens can we have? Well, I can have 2 queens, or 3 queens, or 4 queens. And I'm going to stop there. I can have 6 cards in my hand. There's only 4 queens in the deck, so queens is like my limiting factor. Let's calculate. A is my number of successes in the population. There are only 4 queens in total to choose from, so 4. Choose, how many am I choosing right now? 2 times N minus A. It's a standard deck of cards, so I have 52 minus all my queens. So 48 more cards to choose the rest of the cards from. Choose, and I need 6 cards in my hand. I've already chosen 2, so I need 4. Next one, 4 queens available. I'm choosing 3. For all the rest of the cards, there's 48 cards left to choose from, and I'm choosing 3 for a total of 6 in my hand. And for the last option, there are 4 queens in the deck. I'm choosing all 4 times 48 other cards left, and I need to choose 2 more to finish up my hand. Let's calculate and check. 4, choose 2 times 48, choose 4, gives us, we got some big numbers here. 1,167,480. So 1,167,480. Next, 4 choose 3 times 48 choose 3 is 69,184. And finally, 4 choose 4. It's only one way to do that. And 48 choose 2 is 1128. And if we graciously add all those numbers together, 69,184, 1128, we are going to get a total of 1,237,792 different ways of selecting a hand in cribbage with at least 2 queens. I'm going to leave it there. I hope that was helpful and gave an overview for how to do these case questions.